Where'd we be without our jaws? Jaws represent an amazing evolutionary advantage, allowing us to cut and grind food for consumption and giving us expanded options for possible sources of food. They play a critical role in organismal biology, since mastication, or chewing, makes up the first stage in the process of digesting food into useful components for an animal to use. Powerful jaws make it easier to crush food into bits, expanding the amount of viable food sources for animals, making it possible for them to acquire the nutrients necessary for life. But where did our modern jaw come from? Who had it first? The earliest fish with jaws were called placoderms and date back to the Silurian era, or even the late Ordovician era, around 400 million years ago. Placoderms had armored skulls, heads like dolphins, and bodies like tanks. Their jaw was divided into three parts: the maxilla, the premaxilla, and the dentary. And these three structures are found in the human jaw today. The weird thing about placoderms, though, were these structures they had called the nathal plates, which basically looked like metal sheet cutters. These structures were so strange that scientists thought, surely our jawbones must have a different origin, like an early bony fish, and that placoderms were just a different side branch that eventually went extinct. However, one of these placoderms stands out: Intelognathus primordialis. We'll call him Dave. Dave lived somewhere around 419 million years ago and had the most complex jaw structure of fish at that time. He had the body of a placoderm, but the jaw of a bony fish without that weird nathal plate. This led scientists to believe that placoderms were the ancestors of bony fish. One piece of fossil evidence isn't enough, though. Luckily, in 2013, scientists discovered a 423-million-year-old fish from China called the Qilin Yu rostrata. We'll call him Luke. Luke had a three-part jaw, but he also looked more like a typical placoderm, further supporting the theory that modern vertebrates originated from placoderms. To contextualize what the development of jaws looked like in humans, we must discuss the process of organogenesis. After gastrulation takes place in the early embryonic development of a human, a three-layer embryo is formed. During organogenesis, various regions of the three embryonic germ layers develop into the rudiments of organs. One of these layers, the ectoderm, thickens into a neural plate just above the notochord, or the mesoderm. The edges of the neural plate fold up to create an elongated, hollow neural tube. Neural crest cells pinch off from this neural tube and give rise to many important structures, such as the medulla of the adrenal gland. But what makes the ectoderm significant to Dave and Luke is that the neural crest cells also become bone and cartilage. Neural crest cells are unique to vertebrates and are important in the evolution of the head and jaws. Although paleobiologists originally believed that the jaws in placoderms could not have evolved from bony fish, the discovery of the Intelognathus fossil marks a large shift, as the Intelognathus likely is an intermediary, linking the two groups in jaw evolution. The presence of the three-bone jaw, made of a maxilla, premaxilla, and dentary in Intelognathus, suggests that it was very important in the evolution and development of jaw structures in early vertebrate ancestors, which commonly included three-bone jaws as precursors to more complex jaw structures, which make it easier to hunt for and consume food. So we can thank Dave and Luke for finally showing us where our jaws come from.